In a vast ocean of space, where starlight fades into endless night, there exists a population of worlds that wander alone. These are the rogue planets, celestial bodies cast adrift from their parent stars, traveling through the galaxy in perpetual darkness. They move silently through the cosmic void, neither bound by gravity to a sun nor blessed with the warmth of stellar radiation. They are orphans of the universe, and their story is one of solitude, mystery, and unexpected wonder. Imagine, if you will, a world floating in absolute darkness. No sunrise greets its surface. No sunset paints its skies. There are no seasons here, no cycles of day and night as we know them. The rogue planet drifts through interstellar space, its journey measured not in days or years, but in millions of years as it traverses the spiral arms of the Milky Way galaxy. The temperature on its surface, if it has one, hovers just above absolute zero, around minus 270 degrees Celsius. Any atmosphere it once possessed may have frozen and fallen to the ground as snow, forming strange, exotic ices that coat its surface in layers of methane, nitrogen, and carbon dioxide. Scientists estimate that there may be billions of these wandering worlds in our galaxy alone. Some calculations suggest that rogue planets may actually outnumber stars, making them perhaps the most common type of planetary body in the Milky Way. This remarkable possibility emerged from gravitational microlensing surveys conducted over the past 2 decades, particularly from observations made by NASA's Spitzer Space Telescope and data from ground-based surveys like the Optical Gravitational Lensing Experiment, known as OGLE. These observations detected brief brightening events when a rogue planet passed in front of a distant star, its gravity bending and magnifying the starlight, a phenomenon predicted by Einstein's theory of general relativity. The discovery of these lonely worlds has transformed our understanding of planetary systems. We once believed that planets formed around stars and remained there, held in stable orbits by gravity's gentle hand. But the universe, it seems, is far more dynamic and chaotic than we imagined. Planetary systems are not always peaceful nurseries where worlds grow undisturbed. They can be violent places where gravitational interactions fling planets out of their orbits and into the darkness beyond. Consider the early solar system some 4.5 billion years ago. The sun had just ignited, and around it swirled a disk of gas and dust from which the planets would form. Computer simulations of this era suggest that our solar system may have once contained additional planets, perhaps an ice giant similar to Neptune or Uranus, that was ejected during the chaotic early period known as the Late Heavy Bombardment. This hypothetical planet, sometimes called Planet V or Planet 9 in various models, would now be wandering the galaxy, a rogue world that once called our sun home. The mechanisms that create rogue planets are varied and complex. Some are ejected during the formation of their planetary systems, when gravitational interactions between young planets become unstable. Imagine 3 or 4 massive worlds orbiting close to each other, their gravitational fields tugging and pulling. Eventually, like a game of cosmic billiards, one planet gains enough velocity to escape, while the others settle into more stable orbits. Other rogue planets may form in isolation, condensing from gas and dust in the same way stars do, but never quite gathering enough mass to ignite nuclear fusion. These objects, sometimes called sub-round dwarfs or planetary mass objects, blur the line between planets and failed stars. The closest rogue planet candidate we know of is located approximately 100 light-years from Earth. Designated Sir 2149-0403, this object was discovered in 2012 by astronomers using the Canada-France-Hawaii telescope. With a mass estimated at around 4 to 7 times that of Jupiter, it drifts through space without a parent star, its surface temperature a relatively warm 400 degrees Celsius. heat left over from its formation, slowly radiating into space. Infrared observations revealed its presence, glowing faintly in wavelengths invisible to human eyes, an ember cooling in the cosmic night. As you settle deeper into comfort, imagine yourself aboard a spacecraft approaching such a world. Your vessel moves silently through the void, the only light coming from your instrument panels and the distant, diamond-like stars scattered across the black canvas of space. Ahead, your sensors detect the rogue planet, a massive sphere perhaps twice the size of Jupiter, wrapped in swirling clouds of hydrogen and helium. There is no reflected sunlight to illuminate it, so you rely on infrared cameras to see. The planet glows with its own internal heat, bands of cloud visible as lighter and darker regions in false color images. Great storms rage in its atmosphere, cyclones larger than Earth itself, spinning in the eternal darkness, driven by the planet's rotation and internal heat. The silence is profound. In the vacuum of space, there is no sound, no wind, no whisper of movement. Your spacecraft's instruments register the planet's magnetic field, a powerful magnetosphere generated by the churning of metallic hydrogen deep within its core. This magnetic field extends millions of kilometers into space, creating a protective bubble that deflects cosmic rays and charged particles from interstellar space. If this rogue planet has moons, they would orbit within this magnetic cocoon, perhaps harboring subsurface oceans kept liquid by tidal heating, much like Jupiter's moon Europa in our own solar system. The existence of rogue planets challenges us to expand our definition of where life might exist. We have long assumed that life requires the warmth and energy of a star, but these wandering worlds suggest other possibilities. A rogue planet with a thick atmosphere and significant internal heat could maintain liquid water beneath kilometers of ice. Radioactive decay in the planet's core, combined with tidal forces if moons are present, could provide energy for billions of years. In such hidden oceans, far from any sun, life might emerge and evolve, never knowing the existence of stars or the greater universe beyond its icy shell. This thought carries a certain poetic melancholy, the idea of life existing in complete isolation in a pocket of warmth surrounded by infinite cold. Yet it also speaks to the resilience and adaptability of nature, to the possibility that the universe may be far more inhabited than we ever dreamed, with life taking hold in the most unexpected places. As we close this first chapter of our journey, let your mind drift like these wandering worlds. Float gently through the darkness, feeling the vastness of space around you, the quiet majesty of these planetary orphans. They have traveled so far, witnessed so much of the galaxy, moving through spiral arms and nebulae, past stars being born and stars dying. They are silent witnesses to the cosmos, carrying their secrets through the endless night. To understand the rogue planets, we must journey back to the beginning, to the birth of planetary systems themselves. The story begins in vast molecular clouds, regions of space so dense with gas and dust that they block the light of stars behind them. These stellar nurseries, like the famous Orion Nebula located approximately 1,300 light-years from Earth, are places of creation where gravity slowly gathers material together, pulling it into clumps that grow denser and hotter. Within these clouds, pockets of gas begin to collapse under their own weight. As a pocket contracts, it starts to spin faster, much like a figure skater pulling in their arms during a pirouette. This spinning cloud flattens into a disk, with most of the mass falling toward the center. Over time, hundreds of thousands to millions of years, the center grows so hot and dense that hydrogen atoms begin to fuse into helium. Nuclear fusion ignites, and a star is born. But the story doesn't end there. The disk of material surrounding the young star, called a protoplanetary disk, becomes the birthplace of planets. This disk is composed of gas, mostly hydrogen and helium, mixed with tiny grains of dust made of silicates, carbon compounds, and water ice. These dust grains slowly stick together through a process called accretion. Two grains collide gently and cling to each other through electrostatic forces and van der Waals interactions. These pairs join with others, forming pebbles, then rocks, then boulders. NASA's Spitzer Space Telescope has observed many protoplanetary disks throughout our galaxy, revealing their structure in exquisite detail. These disks can extend for billions of kilometers, with distinct regions where different types of planets form. Close to the star, where temperatures are high, only materials with high melting points can remain solid: metals and rocky minerals. This is where terrestrial planets like Earth and Mars form. Farther out, beyond what astronomers call the frost line, temperatures drop low enough for water ice to remain frozen. Here, planetary embryos can grow much larger because ice is abundant, eventually becoming gas giants like Jupiter and Saturn. But the process is not gentle or orderly. Computer simulations of planetary formation, conducted by researchers at institutions like the Southwest Research Institute and NASA's Ames Research Center, reveal a chaotic picture. As planets grow, they begin to interact gravitationally. A young Jupiter-sized planet can migrate inward toward its star, its gravity stirring up the orbits of other forming planets. These gravitational disturbances can fling smaller planets into eccentric orbits, send them crashing into the star, or eject them from the system entirely. This last fate, ejection into interstellar space, is how many rogue planets are born. Consider a planetary system with 3 or 4 massive planets orbiting relatively close to each other. Their gravitational interactions create a complex dance, sometimes described as a 3-body problem or many-body problem in celestial mechanics. Unlike the stable 2-body problem of a planet orbiting a star, these multi-body systems can be inherently unstable. Small perturbations grow over time until the system reorganizes itself violently. The NICE model, named after the city in France where it was developed, describes such a reorganization in our own solar system's history. According to this model, about 600 million years after the Sun's formation, the giant planets, Jupiter, Saturn, Uranus, and Neptune, underwent a period of orbital instability. Jupiter and Saturn crossed a resonance, a special orbital relationship where their gravitational tugs synchronized, causing their orbits to change rapidly. This event scattered the outer planets, sending Neptune on a long migration outward and scattering countless icy bodies throughout the solar system. Some scientists propose that during this chaotic period, a 5th giant planet may have existed. This ice giant, comparable in size to Uranus or Neptune, was flung out of the solar system entirely during the orbital reshuffling, becoming a rogue planet. While this remains hypothetical, the mathematics of planetary dynamics suggest it's entirely plausible. If such a planet existed and was ejected, it is now thousands of light years away, forever lost to the Sun's family. Rogue planets can also form in a completely different way, through the same process that creates stars, but on a smaller scale. In the denser regions of molecular clouds, some clumps of gas may collapse into objects too small to sustain hydrogen fusion. If such an object has a mass below about 13 times that of Jupiter, the minimum mass needed to fuse deuterium, a heavy isotope of hydrogen, it is classified as a planetary mass object rather than a brown dwarf or star. These isolated planetary mass objects form alone, never part of any planetary system, born into loneliness. The discovery of such objects has been made possible by infrared surveys of star-forming regions. The young planetary mass objects are still warm from their formation, glowing in infrared light even though they emit no visible light. In regions like the Sigma Orionis cluster, about 1,200 light-years from Earth, astronomers have identified several planetary mass objects with masses as low as 3 times that of Jupiter, floating freely among the young stars, unattached to any of them. These discoveries raise fascinating questions about the nature of planets themselves. If an object forms like a star but has the mass of a planet, is it truly a planet? Or is the definition of a planet tied to its formation within a circumstellar disk and its orbit around a star? The International Astronomical Union has grappled with these questions, particularly after the controversial reclassification of Pluto in 2006. For rogue planets, the definition remains somewhat fluid, with astronomers sometimes distinguishing between ejected planets and sub-round dwarfs based on their formation history, even though the objects themselves may be physically identical. As we consider these wandering worlds, born either in violence or in solitude, let your thoughts drift to the nature of belonging and isolation. These planets, whether cast out or never claimed, continue their journeys through the galaxy. They carry with them the chemical signatures of their birthplaces, isotope ratios in their atmospheres that tell of the molecular cloud that spawned them, or the protoplanetary disk where they first coalesced. Imagine the journey of such a world, newly ejected from its system. In its early days as a rogue, it might still be warm, its surface glowing red-hot from the heat of formation and the violence of ejection. Any moons it possessed might still orbit, though some may have been stripped away during the ejection process. Over millions of years, the planet cools, its glow fading from red to infrared to almost nothing. Its atmosphere, if it ever had one, may freeze and fall as snow. But deep within, the core remains hot, heated by radioactive decay and residual heat from formation, warmth that will persist for billions of years. This internal heat is crucial. It means that rogue planets are not completely frozen, dead worlds. They possess their own energy source, independent of any star. This energy drives geological activity, generates magnetic fields, and, perhaps, maintains subsurface oceans where the conditions for life might exist. Let these thoughts carry you deeper into rest. Like a planet settling into its long voyage through the galaxy, its path written in the language of gravity and momentum, destined to wander until the stars themselves grow cold. Finding a planet that emits no light and wanders through the void might seem an impossible task, like searching for a single grain of black sand on a dark beach at midnight. Yet astronomers have developed ingenious methods to detect these invisible wanderers, techniques that rely on fundamental physics and careful observation. The search for rogue planets is a testament to human ingenuity and our deep desire to understand the universe. The primary method used to detect rogue planets is gravitational microlensing, a technique that exploits Einstein's general theory of relativity. According to Einstein's theory, mass warps the fabric of space-time. Much like a heavy ball placed on a stretched rubber sheet creates a depression. When light from a distant star passes near a massive object, the warped space-time causes the light's path to bend. This bending acts like a lens, focusing and magnifying the distant star's light. If a rogue planet passes in front of a background star, from our perspective on Earth, the planet's gravity bends the starlight around it, causing the star to appear brighter for a period of time. This brightening event, called a microlensing event, typically lasts from a few hours to a few days, depending on the mass of the lensing object and its speed across our line of sight. The shape and duration of the brightening curve tell astronomers about the mass and distance of the object causing the lensing. The Optical Gravitational Lensing Experiment, OGLE, has been monitoring millions of stars in the galactic bulge, the central region of our Milky Way, since 1992. Using a telescope at Las Campanas Observatory in Chile, OGLE searches for these brief brightening events. In 2011, a team of astronomers analyzing OGLE data published results suggesting that Jupiter-mass rogue planets might be nearly twice as common as main sequence stars in our galaxy. They identified 10 candidate microlensing events with durations of about 2 days, consistent with free-floating Jupiter-mass objects. However, detecting rogue planets through microlensing is challenging. Each star can only be lensed once by a given object, making these events unique and non-repeatable. Additionally, microlensing cannot distinguish between a planet ejected from a system and a planetary mass object that formed in isolation. Both produce identical signals. The technique also has a mass threshold. It is most sensitive to objects between roughly the mass of Mars and 10 times Jupiter's mass. Objects smaller than Mars or much larger than Jupiter create signals that are either too brief or too long to detect reliably with current surveys. NASA's Nancy Grace Roman Space Telescope, scheduled to launch in the mid-2020s, is designed to detect thousands of exoplanets using microlensing. With a field of view 100 times larger than Hubble's infrared camera and the ability to monitor the galactic bulge continuously, Roman will revolutionize our understanding of rogue planets. Simulations suggest it could detect hundreds or even thousands of free-floating planets, including objects as small as Mars and as large as superjupiters, providing the first comprehensive census of this population. Another approach to finding rogue planets involves direct imaging in infrared wavelengths. Young rogue planets, those less than about 100 million years old, still glow with heat from their formation. This thermal radiation is brightest in the infrared part of the spectrum, invisible to human eyes but detectable with specialized instruments. Infrared surveys of star-forming regions have revealed several young planetary mass objects glowing softly in the darkness. The Wide-Field Infrared Survey Explorer, WISE, launched by NASA in 2009, surveyed the entire sky in infrared light. Although designed primarily to find asteroids and study distant galaxies, WISE data has been used to search for nearby rogue planets. In 2011, astronomers announced the discovery of CFSR 2149-0403 using data from WISE combined with ground-based observations. This object, located approximately 100 light-years away, has a temperature around 400 degrees Celsius and a mass between 4 and 7 Jupiter masses, making it one of the closest known planetary mass objects to Earth. Direct imaging has limitations, though. It can only detect relatively warm objects, which means young planets or very massive ones that retain more internal heat. Older rogue planets, cooled to temperatures near absolute zero, become virtually invisible in all wavelengths. They lurk in the darkness, detectable only through their gravitational influence on light from more distant sources. Radio observations offer another potential detection method. Some rogue planets might generate strong auroral emissions, similar to the intense radio signals produced by Jupiter's magnetic field. On Jupiter, charged particles from the solar wind interact with the planet's powerful magnetosphere, creating brilliant auroras at the poles and emitting radio waves that can be detected from Earth. A rogue planet with a strong magnetic field might produce similar emissions, though the absence of stellar wind means the mechanism would be different, perhaps driven by interactions with moons or cosmic rays. The Square Kilometre Array, an international radio telescope project currently under construction in Australia and South Africa, will have the sensitivity to detect radio emissions from nearby rogue planets. When completed, it will be the world's largest radio telescope, capable of mapping the sky with unprecedented detail. If rogue planets do produce detectable radio emissions, SKA will find them. As you contemplate these detection methods, consider the patience required. Astronomers must monitor millions of stars for years, watching for a brief flicker that might indicate a rogue planet crossing our line of sight. They must sift through enormous data sets, distinguishing genuine signals from instrumental noise and other transient phenomena. It is painstaking work, requiring dedication and attention to detail, but each discovery adds another piece to the cosmic puzzle. Imagine sitting in an observatory control room, the darkness outside complete except for the stars. Your eyes are fixed on a computer screen displaying light curves, graphs showing the brightness of stars over time. Most are flat, unchanging lines, the steady light of distant suns. But then, one line begins to rise, a smooth increase in brightness over the course of hours. Your heart quickens. You check and recheck the data, running algorithms to rule out instrumental errors or variable star phenomena. The signal holds. The shape matches the theoretical prediction for a microlensing event caused by an object several times Jupiter's mass. Somewhere between your telescope and that distant star, a rogue planet has passed, its gravity momentarily focusing starlight in your direction. A cosmic lighthouse flashing once, then fading back into darkness. The planet itself is invisible to you and always will be. It is too far, too dark, too cold to see. But its presence is undeniable, written in the language of gravity and light. This invisible wanderer, perhaps ejected from its birth system billions of years ago, has revealed itself for a few hours before continuing its lonely journey. You have witnessed evidence of a world that may never be directly observed, a planet that exists in perpetual night. This is the nature of modern astronomy, discovering unseen worlds through their subtle influences, reading the universe's secrets in patterns of light and gravity. It requires both technological sophistication and a certain humility, an acceptance that we cannot always see what we study, that some truths must be inferred rather than directly observed. Let this thought accompany you into deeper rest, the idea that understanding doesn't always require seeing, that presence can be known through effect, and that even in darkness, gravity connects all things, weaving an invisible web that binds the cosmos together. What would it be like to stand on the surface of a rogue planet? The question invites us into a realm of imagination grounded in physics, a thought experiment that helps us understand these strange worlds. Picture yourself on such a world, your feet planted on solid ground, or perhaps on frozen ice, beneath a sky of absolute blackness, unrelieved by sun, moon, or even the glow of a distant galaxy. The first sensation would be the cold. Rogue planets far from any star reach temperatures approaching cosmic background radiation, about 2.7 Kelvin or minus 270 degrees Celsius, just barely above absolute zero. At these temperatures, most substances we know freeze solid. Nitrogen, oxygen, carbon dioxide, even methane, all exist as ice. If you removed your glove for even a second, your hand would freeze so rapidly that the moisture in your skin would crystallize instantly. Yet not all rogue planets are completely frozen. Those with substantial mass retain heat from their formation for billions of years. Radioactive elements in the planet's interior, uranium, thorium, potassium, decay slowly, generating warmth. A rogue planet several times Earth's mass, with a composition similar to our world's, would have a molten core billions of years after its ejection, kept liquid by radioactive decay and residual formation heat. This internal heat can have profound effects. On Earth, our planet's internal heat drives plate tectonics, volcanism, and a geodynamo that generates our magnetic field. A massive rogue planet might experience similar processes. Volcanic activity could puncture through its frozen crust, releasing heat and gas from the interior. These eruptions, occurring in complete darkness, would be invisible except in infrared wavelengths, glowing vents of warmth in a frozen landscape, creating local environments where temperatures rise above freezing for brief periods. Water ice, if present in large quantities, might melt beneath the surface due to this internal heat. Consider Europa, Jupiter's moon, located in our solar system. Europa's surface is covered in water ice, but tidal heating from Jupiter's gravity keeps a vast ocean liquid beneath the icy shell. A massive rogue planet could maintain subsurface oceans through its own internal heat alone, without needing tidal forces. These oceans, trapped between ice above and rocky core below, would exist in complete darkness, insulated from the frigid vacuum of space. The sky above a rogue planet would be remarkable, without atmospheric scattering of light, there being no nearby sun to scatter. And with minimal air, if the atmosphere has frozen and fallen as snow, the stars would appear with extraordinary clarity. Thousands of stars, perhaps tens of thousands, depending on the rogue planet's location in the galaxy, would be visible as perfect, unwavering points of light. The Milky Way's band would stretch across the sky, a river of starlight marking the plane of the galaxy. From certain rogue planets, particularly those ejected from systems near the galactic core, the view would be spectacular. The central bulge of the Milky Way would dominate the sky, a vast cloud of billions of stars compressed into a relatively small area. This region, located about 26,000 light-years from Earth, contains stars of all ages, some as old as the galaxy itself, packed so densely that the night sky from such a vantage would glow with their combined light. Not enough to illuminate the landscape, but enough to render the darkness a deep blue-black rather than pure black. If the rogue planet retained moons, they too would orbit in darkness, without sunlight to illuminate them. These moons would be visible only by reflected starlight, faint gray shapes moving against the star field, detectable more by their occultation of stars than by any light of their own. The tidal forces between a rogue planet and its moons would generate heat through flexing, similar to the mechanism that keeps Europa's ocean liquid. These moons might be the most geologically active places in the system, with subsurface oceans of their own, perhaps even volcanic activity on their surfaces. The magnetic field of a massive rogue planet would create a magnetosphere, an invisible bubble in space that deflects charged particles and cosmic rays. This magnetic field, generated by the motion of electrically conductive fluids in the planet's core, would extend far beyond the atmosphere, protecting any moons from radiation. On Earth, our magnetic field channels charge particles from the solar wind toward the poles, where they collide with atmospheric gases and create the aurora, the northern and southern lights. A rogue planet might experience similar phenomena, though driven by cosmic rays and the interstellar medium rather than stellar wind. These auroras, shimmering curtains of light in the darkness, would be the only illumination on the planet's surface besides volcanic glow and starlight. Gravity on a rogue planet varies depending on its mass and radius. A planet twice Earth's mass, but similar in radius, would have surface gravity about twice what we experience. Walking would be difficult, and standing for long periods exhausting. Conversely, a low-density gas giant, even if massive, might have relatively low surface gravity, assuming it has a surface to stand on, which gas giants typically don't. Jupiter, for instance, has no solid surface. Descending through its atmosphere, you would encounter gas that grows denser and hotter until it transitions to a fluid state, then eventually to exotic forms of matter like metallic hydrogen under immense pressure. Imagine descending through the atmosphere of a rogue gas giant. Your spacecraft penetrates the outer cloud layers, composed of frozen ammonia crystals. Deeper down, you encounter decks of water ice clouds, then layers of ammonium hydrosulfide. The temperature rises as you descend, warmed by the planet's internal heat. Lightning flashes in the clouds, electrical discharges caused by the churning of atmospheric gases and the friction between cloud layers. These storms, larger than Earth itself, rage in perpetual darkness, their lightning the only light they've known for millions of years. Deeper still, the hydrogen gas around your spacecraft becomes denser, transitioning from gas to liquid. The pressure rises to millions of times Earth's atmosphere pressure. Your spacecraft, if it could survive these conditions, would eventually reach a layer where hydrogen becomes so compressed that its electrons break free from atoms, allowing it to conduct electricity like a metal. This metallic hydrogen layer, existing nowhere naturally on Earth, is responsible for generating the planet's powerful magnetic field. At the very core, perhaps thousands of kilometers down, might be a solid center, a sphere of rock and metal several times Earth's mass, heated to temperatures of 10,000 degrees Celsius or more. This core, though hot, never sees light, buried as it is beneath layers of hydrogen thousands of kilometers thick. It is a furnace in the abyss, a heart of heat in a body wandering the cold void. As you rest, let your mind explore these hidden realms, the subsurface oceans under kilometers of ice, lit only by the dim glow of hydrothermal vents, the metallic hydrogen seas generating magnetic fields in the darkness, the frozen surfaces beneath skies full of stars. These worlds, though isolated and dark, are not simple or dead. They are complex, dynamic, driven by forces from within, carrying on their slow processes even without the benefit of a sun. In this way, they remind us that energy and activity don't require light, that existence continues in all conditions, and that the universe is full of hidden wonders waiting to be understood. How many rogue planets wander through our galaxy? This question, simple to ask but profoundly difficult to answer, drives much of the current research into these mysterious objects. The answer has implications not just for astronomy, but for our understanding of planetary formation, the evolution of planetary systems, and even the possibility of life beyond Earth. Early estimates, based on microlensing observations from the OGLE survey, suggested that Jupiter-mass rogue planets might outnumber stars in the Milky Way. A 2011 study, analyzing 10 candidate microlensing events, extrapolated that there could be approximately 2 Jupiter-mass free-floating planets for every main sequence star in the galaxy. Given that our galaxy contains roughly 200 billion to 400 billion stars, this would imply hundreds of billions of rogue planets, a staggering number. However, subsequent analyses have been more conservative. The challenge lies in interpreting microlensing data. A brief microlensing event could be caused by a rogue planet, but could also be caused by a planet orbiting far from its host star, so far that the star's light doesn't affect the microlensing signal. Distinguishing between these scenarios requires careful analysis of the light curve's detailed shape and, ideally, follow-up observations, which are difficult because microlensing events are unique and non-repeating. A 2017 study using data from the Korean Microlensing Telescope Network, KIM-TNET, analyzed hundreds of microlensing events and concluded that the frequency of Jupiter-mass free-floating planets is roughly 1/4 to 1/2 that of main sequence stars, still a very large number, but more modest than earlier estimates. This suggests tens of billions to over 100 billion Jupiter-mass rogue planets in the Milky Way. But Jupiter-mass planets are just one category. Theoretical models of planetary formation suggest that smaller planets, those closer to Earth's mass or Neptune's mass, might be ejected even more frequently than gas giants. During the chaotic early stages of a planetary system, when planets are still forming and orbits are unstable, lighter objects are easier to accelerate to escape velocity than massive ones. This implies that for every Jupiter-mass rogue planet, there might be several Neptune-mass or Earth-mass rogues. If this is true, the total population of rogue planets could number in the trillions. This would make them by far the most common type of planetary body in the galaxy, vastly outnumbering planets in stable orbits around stars. The implications are humbling. The image we have of the galaxy as a collection of stars with planetary systems would be incomplete. Instead, the space between stars would be filled with a vast population of wandering worlds, invisible and silent, drifting through the darkness. Detecting smaller rogue planets is extremely challenging with current technology. Microlensing events caused by Earth-mass objects last only hours, sometimes less, and require continuous monitoring of millions of stars to catch. NASA's Nancy Grace Roman Space Telescope, with its wide field of view and continuous monitoring capability, will be essential for this. Simulations predict that Roman could detect dozens to hundreds of Earth-mass rogue planets during its mission, providing the first direct constraints on the population of small rogues. Another approach involves studying young, star-forming regions directly. In regions like the Trapezium cluster in Orion, about 1,500 light-years from Earth, thousands of stars are forming from collapsing clouds of gas and dust. Among these stars are planetary mass objects, detected through infrared observations. These objects, with masses as low as a few times that of Jupiter, are too small to be stars but appear to be forming in isolation rather than in circumstellar disks. The distinction between these isolated planetary mass objects and true rogue planets, those ejected from planetary systems, is important for understanding how they form. Objects that form like stars through the collapse of gas clouds have different chemical compositions and physical properties than planets that form in circumstellar disks and are later ejected. Distinguishing between these two populations observationally is difficult but crucial for refining our models of star and planet formation. Infrared surveys, such as those conducted by the Spitzer Space Telescope and the European Space Agency's Herschel Space Observatory, have cataloged thousands of young stellar objects in nearby, star-forming regions. Among these are several hundred planetary mass candidates, objects that glow faintly in the infrared due to heat from their recent formation. Studying the distribution and properties of these objects helps astronomers understand how common different formation pathways are. One intriguing discovery from these surveys is that some planetary mass objects in star-forming regions have circumplanetary disks, rings of gas and dust orbiting the object, similar to protoplanetary disks around young stars, but on a smaller scale. These disks might form moons, creating systems in miniature where a rogue planetary mass object becomes the center of its own tiny planetary system. The existence of such systems suggests that even in isolation, the processes of accretion and satellite formation can occur, given sufficient material. The chemical composition of rogue planets provides clues about their origins. Planets that form in circumstellar disks incorporate elements and ratios that reflect the temperature and pressure conditions of different regions in the disk. The ratio of carbon to oxygen, for example, varies depending on where in the disk a planet forms relative to various snow lines, distances from the star where different volatile compounds freeze. A planet that forms beyond the water snow line will have different chemical signatures than one that forms inside it. Spectroscopic observations of young, rogue planetary mass objects can reveal their atmospheric compositions. If an object's atmosphere is enriched in heavy elements compared to the interstellar medium, this suggests it formed from a circumstellar disk. If its composition matches the interstellar medium more closely, it might have formed through direct collapse like a star. Future observations with the James Webb Space Telescope, launched in 2021, will provide detailed spectra of these objects, helping to answer questions about their formation. As we contemplate these vast numbers, trillions of worlds drifting in darkness, consider the statistical likelihood that one might pass relatively near our solar system. Relatively near in cosmic terms might mean within a few light years, close enough for our telescopes to study in detail. Calculations suggest that over the course of Earth's history, several rogue planets may have passed within a few light years of the Sun, though none close enough to disrupt the orbits of our planets. Calculations suggest that over the course of Earth's history, several rogue planets may have passed within a few light years of the Sun, though none close enough to disrupt the orbits of our planets. There's even a small but non-zero probability that a rogue planet might be captured by the Sun's gravity, becoming a new member of our solar system. Such an event would require very specific conditions. The rogue planet would need to pass close enough to interact gravitationally with an existing planet, losing enough velocity to become gravitationally bound to the Sun. This is essentially the reverse of the ejection process, and while rare, it's not impossible. Some astronomers have speculated that the hypothetical Planet 9, a large planet proposed to exist in the outer solar system based on the unusual orbits of distant Kuiper Belt objects, could actually be a captured rogue planet rather than one that formed with our solar system. This idea remains controversial and unproven, but it illustrates how rogue planets could, in principle, join new stellar systems long after their initial formation. As you drift towards sleep, imagine the galaxy as a vast ocean, with stars as islands of light scattered across it. Between these islands, currents of gravity and motion carry countless worlds through the darkness, each on its own trajectory, each with its own history. They pass near each other, sometimes interacting, sometimes continuing on without ever knowing another world was nearby. It's a dynamic, ever-changing landscape, invisible to the eye, but revealed through patience and careful observation, a hidden population that outnumbers the visible stars themselves. In the darkness of interstellar space, far from the warmth and radiation of any star, the chemistry of a rogue planet takes on unique characteristics. Without stellar ultraviolet light to drive photochemical reactions in its atmosphere, and with surface temperatures near absolute zero, the chemical processes that occur on these worlds differ fundamentally from those on planets orbiting stars. Yet chemistry continues, driven by cosmic rays, radioactive decay, and the planet's internal heat, a slow, patient chemistry of isolation. Consider the atmosphere of a rogue planet, if it retains one. When a planet is ejected from its system, the atmosphere it carries with it begins to cool. Gases that exist at high temperatures condense and freeze. On Earth, our atmosphere is composed primarily of nitrogen and oxygen, with smaller amounts of argon, carbon dioxide, and water vapor. Were Earth somehow removed from the sun's influence and placed in interstellar space, our atmosphere would undergo dramatic changes. Water vapor would condense first, forming clouds, then rain, then snow, as temperatures plummeted. This water ice snow would accumulate on the surface, perhaps forming layers kilometers thick over millions of years. Next, carbon dioxide would freeze out of the atmosphere at temperatures below minus 78 degrees Celsius, forming dry ice snow. At even lower temperatures, around minus 200 degrees Celsius, nitrogen would begin to condense, eventually freezing at minus 210 degrees Celsius. Oxygen would freeze at minus 218 degrees Celsius. If the cooling continued until the planet reached thermal equilibrium with the cosmic microwave background, 2.7 Kelvin, only the lightest elements would remain gaseous, hydrogen and helium. Everything else would have frozen solid and fallen to the surface as exotic snows. Methane snow, nitrogen snow, oxygen snow, forming layers upon layers of colorful ices coating the planet's crust. However, a massive rogue planet with substantial internal heat might retain a gaseous atmosphere indefinitely. The heat radiating from the planet's interior warms the lower atmosphere, creating a temperature gradient. Near the surface, where internal heat keeps temperatures above freezing points of major volatiles, the atmosphere remains gaseous. Higher up, where it's colder, gases condense and form clouds, which then precipitate back down, creating a weather cycle driven entirely by internal heat rather than stellar radiation. Such an atmosphere would be in a state of slow convection. Warm gases rise from near the surface, carrying heat upward. As they rise and cool, they become denser and sink again, creating circulation cells similar to those on Earth or Jupiter, but without the complicating factor of solar heating creating day-night temperature differences. The weather on such a world would be driven purely by the planet's rotation and internal heat distribution, creating stable, long-lasting storm systems. The chemistry occurring in these atmospheres will be fascinating. Cosmic rays, high-energy particles from supernovae and other energetic events across the galaxy, constantly bombard rogue planets. These particles penetrate deep into atmospheres, ionizing molecules and creating free radicals, chemically reactive molecular fragments. These radicals can then recombine in various ways, creating complex organic molecules. Laboratory experiments and computer simulations have shown that even without stellar ultraviolet light, cosmic ray-driven chemistry can produce amino acids, nucleobases, and other prebiotic molecules from simple starting materials like methane, ammonia, and water. This process, called cosmic ray spallation chemistry, could occur in the upper atmospheres of rogue planets, slowly creating a rich inventory of organic compounds that settle through the atmosphere and accumulate on the surface or in subsurface oceans. Speaking of subsurface oceans, these represent perhaps the most chemically interesting environments on rogue planets. An ocean trapped beneath kilometers of ice, kept liquid by tidal heating or radioactive decay in the planet's core, would be in contact with rocky material at the ocean floor. Water interacting with rock at elevated temperatures drives hydrothermal chemistry, similar to what occurs at seafloor hydrothermal vents on Earth. On Earth, hydrothermal vents support remarkable ecosystems based not on photosynthesis, but on chemosynthesis, the extraction of chemical energy from reactions between seawater and volcanic rock. Microorganisms oxidize hydrogen sulfide, methane, or hydrogen gas, using the energy released to build organic molecules from carbon dioxide. These microorganisms form the base of a food chain that includes tube worms, clams, and other complex organisms, all thriving in complete darkness, independent of the sun's energy. A rogue planet's subsurface ocean could support similar chemosynthetic ecosystems. The chemistry would be driven by water-rock interactions at the interface between the ocean and the rocky mantle. Serpentinization, a process where water reacts with iron-rich minerals like olivine, produces hydrogen gas and heat. Microorganisms could use this hydrogen as an energy source, supporting a biosphere in eternal darkness. The salinity and chemistry of a rogue planet's ocean would depend on the rock composition and the ocean's age. Over billions of years, minerals would dissolve into the water, potentially creating a very saline ocean, perhaps even supersaturated with salts in some regions. Conversely, if the ocean is in contact with clay minerals that remove ions from solution, it might be relatively fresh. The pH could range from acidic to alkaline, depending on dissolved gases like carbon dioxide or ammonia. Radioactive elements dissolved in the ocean or embedded in the rocky crust would undergo decay, releasing energy and particles. Uranium-238, with a half-life of 4.5 billion years, and thorium-232, with a half-life of 14 billion years, decay through chains of reactions, each step releasing alpha or beta particles and gamma rays. These particles can break apart water molecules in a process called radiolysis, creating hydrogen peroxide, free oxygen, and hydrogen gas, all useful for supporting chemical reactions and potentially life. Europa, Jupiter's moon, is thought to have a subsurface ocean where radiolysis from Jupiter's intense radiation environment creates oxidants that could support metabolism. A rogue planet, though not experiencing radiation from a host planet, could have similar processes occurring from cosmic rays penetrating its icy shell and from radioactive decay within the ocean and crust. The ice shell itself would have interesting chemistry. Different types of ice, stable at different pressures and temperatures, create distinct layers. Near the surface, water ice in its familiar hexagonal form, ice IH, would dominate. Deeper down, under pressure from overlying ice, different crystalline structures form. Ice 2, Ice 3, Ice V, Ice 6, each with different properties. At even greater depths, Ice 7 forms, a cubic structure stable at pressures above 2 gigapascals. These high-pressure ice layers could trap gases and organic molecules, preserving them for billions of years. If the rogue planet once orbited a star and had surface life or complex chemistry before ejection, Evidence of that history might be frozen into the ice layers, a geological record waiting to be read if anyone ever explores such a world. The surface ice would be modified by cosmic rays over time. High-energy particles striking water ice can break molecular bonds, creating oxygen, hydrogen peroxide, and ozone even without liquid water or atmospheric oxygen. This process, observed on icy moons like Europa and Ganymede, could give rogue planet surfaces a thin veneer of oxidized chemistry, a frozen record of billions of years of cosmic ray bombardment. Let these chemical processes accompany you into deeper rest. Slow reactions in frozen atmospheres, molecules tumbling through convection currents, water flowing over rock in absolute darkness, creating and transforming, endlessly patient. Chemistry, like existence itself, continues regardless of light, driven by energy and entropy, finding pathways and equilibria in every environment. Could life exist on a rogue planet? This question, speculative yet grounded in our understanding of biology and planetary science, opens fascinating possibilities. Life on Earth requires three fundamental things: liquid water, chemical energy, and organic molecules. Rogue planets, despite their isolation and darkness, might provide all three. The key is liquid water. On Earth, life exists wherever liquid water is found, from Antarctic ice sheets to deep ocean trenches to hot springs in volcanic regions. The presence of water in liquid form appears to be the critical requirement, more important than temperature range, light, or any other factor. Life has adapted to survive in temperatures from minus 15 degrees Celsius in supercooled water droplets to above 120 degrees Celsius in deep-sea hydrothermal vents. It thrives in complete darkness, in acidic pools, in salt-saturated brine, and in solid rock kilometers underground. A rogue planet with a subsurface ocean would have liquid water in abundance. If the planet is massive enough, perhaps several times Earth's mass, radioactive decay in its core would generate heat for billions of years. Combined with an insulating layer of ice on top, this heat could maintain liquid water even in the absence of stellar radiation. The ocean might be hundreds of kilometers deep, contained between an icy crust above and a rocky mantle below, existing in stable conditions for geological timescales. Energy is the next requirement. On Earth's surface, the sun provides energy through photosynthesis, which converts light into chemical energy stored in organic molecules. But in the deep ocean and underground, where light never penetrates, life has evolved chemosynthesis, using chemical reactions to extract energy. At hydrothermal vents, microorganisms oxidize hydrogen sulfide or hydrogen gas, converting them to sulfate or water while capturing the released energy. A rogue planet's ocean floor could have similar hydrothermal activity. Water circulating through cracks in the rocky crust would be heated by the planet's interior, causing it to rise and emerge from vents carrying dissolved minerals and gases. The temperature contrast between hot vent fluid and cold ocean water would drive chemical reactions. Hydrogen gas, produced by serpentinization of iron-rich rocks, could serve as an energy source for microbial metabolism. Serpentinization is particularly interesting because it occurs without requiring high temperatures. When water reacts with olivine, a common mineral in planetary mantles, it produces serpentine minerals, magnetite, and hydrogen gas. This reaction is exothermic, meaning it releases heat, and it can occur at temperatures as low as 50 degrees Celsius. The hydrogen gas produced is an excellent energy source for certain types of bacteria called methanogens, which combine hydrogen with carbon dioxide to produce methane and water, capturing the released energy. Organic molecules, the building blocks of life, could form through several mechanisms on a rogue planet. Cosmic ray-driven chemistry in the atmosphere could create amino acids and other organics, which would eventually settle into the ocean. Hydrothermal chemistry could synthesize organics from carbon dioxide and hydrogen. If the planet carried organic material from its time orbiting a star, this material would be preserved in the ice or dissolved in the ocean. The Miller-Urey experiment, conducted in 1952, demonstrated that amino acids form readily when simple gases like methane, ammonia, and hydrogen are exposed to energy sources like electrical sparks simulating lightning. Similar chemistry could occur in the turbulent atmospheres of rogue planets or near hydrothermal vents, gradually enriching the ocean with organic compounds. Consider the possibility of life evolving in such an ocean. The first organisms would be simple, single-celled microbes using chemical energy to build and maintain their structures. Over millions or billions of years, evolution could produce more complex forms. Without light, photosynthesis would never evolve, so all life would be chemosynthetic or heterotrophic, consuming organic molecules or living symbiotically with chemosynthetic microbes. An ecosystem might develop around hydrothermal vents, similar to those on Earth's ocean floor. Microbial mats of chemosynthetic bacteria would coat the rocky surfaces near vents, converting hydrogen and carbon dioxide into biomass. Larger organisms, perhaps analogous to tube worms or clams, could evolve to host these bacteria in their tissues, gaining nutrition from their symbionts. Predators and scavengers could follow, creating a food web based entirely on chemical energy from the planet's interior. Such a biosphere would be limited in extent and productivity compared to Earth's sunlit ecosystems. The energy available from hydrothermal chemistry is much less than from photosynthesis. Earth's hydrothermal vent ecosystems are small oases in a vast desert of the deep ocean floor. Similarly, a rogue planet's life might be concentrated near active geological features, with vast regions of the ocean remaining barren. However, the stability of the environment could favor the persistence of life over geological timescales. On Earth, mass extinctions have been caused by asteroid impacts, volcanic eruptions, and climate changes, many linked to external factors like the planet's position relative to the Sun or events in the solar system. A rogue planet's subsurface ocean would be largely immune to such disruptions. No asteroids could penetrate kilometers of ice to strike the ocean. No solar storms or stellar flares would affect conditions. The environment would remain remarkably constant, changing only gradually as the planet's interior cools over billions of years. This stability might allow evolution to produce complex adaptations even without high energy availability. Slow, efficient metabolisms could evolve, with organisms living for centuries or millennia, reproducing rarely but with high success rates. The ocean's chemistry might facilitate long-term information storage and transmission, perhaps through unusual mechanisms we haven't imagined. Communication in such an ocean would not involve light, since no organisms could evolve vision in absolute darkness. Sound, chemical signals, electrical fields, or pressure waves might serve as communication methods. Some Earth organisms, like elephants and whales, use low-frequency sounds that travel long distances through rock and water. Rogue planet organisms might develop similar long-range communication, sharing information across vast ocean regions. The discovery of life on a rogue planet would profoundly change our understanding of life's prevalence in the universe. If life can exist and evolve without a star, independent of stellar energy, then the number of potentially inhabited worlds increases dramatically. Instead of being limited to planets in the narrow, habitable zones around stars where surface water remains liquid, life could exist in the far more numerous population of rogue planets and moons with subsurface oceans. This possibility has led some scientists to propose that the majority of life in the universe might exist in dark, hidden oceans beneath ice, far from any star. These biospheres, though isolated and invisible, could collectively host more biomass and more species than all the sunlit worlds combined. Life, rather than being a rare phenomenon requiring special conditions, might be common wherever liquid water and chemical energy coincide, regardless of light. As you consider these hidden biospheres drifting through the galaxy in their ice-encased worlds, let your thoughts turn to the nature of life itself. Its resilience, its adaptability, its ability to find footholds in the most unlikely places. From scorching volcanic vents to frozen Antarctic lakes, from acidic springs to the dry valleys of the Atacama Desert, life on Earth has demonstrated remarkable tenacity. Why should the darkness of a rogue planet's ocean be any different? Perhaps in that darkness, in the slow chemistry of rock and water, in the patient circulation of thermal currents, life has found a way to exist, to persist, to evolve, carrying on its quiet existence unknown and unobserved, a secret held by the wandering dark. In the vast emptiness of interstellar space, the probability of any two objects encountering each other might seem vanishingly small. Yet over the billions of years that galaxies exist, rare events become inevitable. Rogue planets occasionally pass near stars, sometimes close enough for gravitational interactions that change both object trajectories. Even rarer, a rogue planet might be captured by a star's gravity, joining a planetary system as a newcomer, carrying with it the secrets of its long journey through the void. The dynamics of planetary capture are governed by the laws of orbital mechanics first described by Johannes Kepler and refined by Isaac Newton. For a rogue planet to be captured by a star, it must lose enough velocity during its encounter that it becomes gravitationally bound. In a two-body system, just a star and a rogue planet, this is impossible. The planet approaches, swings around the star in a hyperbolic trajectory, and departs with the same speed it arrived, just in a different direction. However, a three-body interaction can lead to capture. If the rogue planet encounters a star that already has planets, gravitational interactions with those planets can remove energy from the rogue's orbit. Imagine a rogue planet entering our solar system on a trajectory that brings it near Jupiter. As it approaches, Jupiter's gravity accelerates it, but in doing so, Jupiter itself recoils slightly, losing a tiny amount of orbital energy. If the encounter geometry is just right, the rogue planet can lose enough speed that it becomes bound to the Sun, while Jupiter's orbit expands slightly to conserve total energy and angular momentum. Such captures are rare, but not impossible. Simulations run by planetary scientists at institutions like the University of Leiden and the Harvard-Smithsonian Center for Astrophysics suggest that during a star's lifetime, it might capture one or two rogue planets if it passes through a dense region of the galaxy, like a star cluster. In our solar system's early history, when the Sun was still part of its birth cluster, the probability of capturing a rogue planet would have been higher than it is now, as the Sun drifts through the relatively empty regions between spiral arms. Some astronomers have proposed that certain unusual objects in our solar system might be captured rogues. The hypothetical Planet 9, if it exists, could be a captured ice giant rather than one that formed with our solar system. Its proposed orbit, highly elliptical and inclined relative to the other planets, would be consistent with capture. Similarly, Triton, Neptune's largest moon, orbits in the opposite direction to Neptune's rotation, suggesting it was captured rather than forming in place. While Triton was most likely captured from the Kuiper Belt rather than from interstellar space, it demonstrates that capture is possible. When a rogue planet is captured, it typically enters a highly elliptical orbit, spending most of its time far from the star and making brief close passes at perihelion, its closest approach. Over millions of years, gravitational interactions with other planets can circularize this orbit, pulling the rogue into a more stable, circular path. Alternatively, the captured planet might remain in its elliptical orbit indefinitely, becoming an oddball member of the planetary system. A rogue planet passing near a star, even if not captured, could have observable effects. If it passed through the inner system, its gravity could perturb the orbits of planets and asteroids, potentially sending some asteroids onto collision courses with inner planets. Such an event might trigger a brief but intense period of impacts, similar to the late heavy bombardment that occurred in our solar system about 4 billion years ago, though that event is now thought to have been caused by the migration of the giant planets rather than a rogue planet encounter. Observations of other stellar systems have revealed some planets in unusual orbits that might be explained by past encounters with rogue planets. Hot Jupiters, gas giants orbiting very close to their stars with periods of just days, are thought to have formed farther out and migrated inward, possibly due to gravitational interactions with other planets or with the protoplanetary disk. Some of these interactions might have involved rogue planets passing through the system during its formation, stirring up the dynamics and causing migrations. From a rogue planet's perspective, an encounter with a star would be a dramatic event after millions or billions of years of isolation. As it approached, the star's gravity would accelerate it, and for the first time since its ejection, the rogue would experience increasing temperatures. If the close approach brought it within a few astronomical units of the star, comparable to the distance from the Sun to Mars or Jupiter, the rogue's surface would begin to warm. Frozen ices that had accumulated over eons would start to sublimate, releasing gases and creating a temporary atmosphere. If the rogue had a subsurface ocean beneath an icy crust, the heat could cause the ice to crack and melt, potentially releasing water vapor and dissolved gases. For a brief period, perhaps a few years to a few decades, depending on the trajectory, the rogue planet would be active, outgassing and warming before swinging back out into the cold darkness. Such an encounter might be observable from Earth if it occurred nearby, within a few hundred light years. Infrared telescopes would detect the warming rogue planet as it brightened during its close approach to the star. Spectroscopic observations could reveal the composition of gases being released from its surface, providing a unique window into the chemistry of a world that formed in one stellar system and spent billions of years in isolation before encountering another. The frequency of close encounters between rogue planets and stars depends on the local density of both populations. In a galactic disk, where most stars reside, the average distance between stars is several light years, and the density of rogue planets is uncertain, but possibly quite high. Statistical models suggest that a typical star like the Sun might have a close encounter with a Jupiter-mass rogue planet every few billion years. Rare on human timescales, but common over the lifetime of the galaxy. In denser environments like globular clusters, where hundreds of thousands of stars are packed into a region only a few tens of light years across, encounters would be far more frequent. Stars in such clusters might experience multiple rogue planet encounters during their lifetimes, and the probability of capture would be correspondingly higher. These clusters, orbiting in the halo around the Milky Way's disk, could harbor planetary systems with mixed populations of native planets and captured rogues, creating complex and dynamic orbital architectures. As you drift into sleep, imagine the gentle arcs of gravitational interaction, the slow dance of massive bodies in space responding to each other's presence. Picture a rogue planet, dark and cold, approaching a distant star, its trajectory bending as gravity takes hold, pulling it into a long ellipse that carries it around the star and back out into darkness. The encounter lasts mere years from the perspective of the universe, but in that brief time, two wanderers acknowledge each other's existence before continuing their separate journeys, one bound to its orbit, one free to roam the galaxy, both following the invisible lines of gravity that connect all things. The future of rogue planet research promises revolutionary discoveries. New telescopes and observational techniques, some already under construction and others in development, will transform our understanding of these wandering worlds. Within the next decade, we will move from detecting handfuls of rogue planets to cataloging thousands, mapping their distribution across the galaxy, and perhaps even characterizing their atmospheres and surfaces. The Nancy Grace Roman Space Telescope, named after NASA's first chief astronomer, is scheduled to launch in the mid-2020s. Roman's primary mission includes a comprehensive microlensing survey of the galactic bulge, monitoring hundreds of millions of stars continuously for several months. Simulations predict that this survey will detect between 200 and 1,000 rogue planets, ranging in mass from Mars-sized to several times Jupiter's mass. This dataset will provide the first statistically robust census of the rogue planet population. Roman's wide-field infrared camera covers an area of sky 100 times larger than Hubble's infrared camera in a single image, making it uniquely suited for microlensing surveys. The telescope will observe the same region of the galactic bulge repeatedly, catching the brief brightening events caused by planets passing in front of background stars. By analyzing the duration and shape of these microlensing events, astronomers will determine the masses and distances of the lensing planets with unprecedented precision. Beyond microlensing, Roman will conduct direct imaging surveys of nearby young star-forming regions, searching for warm, recently formed rogue planets that still glow in infrared light. These observations will complement microlensing by providing information about the youngest rogues, those less than 100 million years old, helping astronomers understand the ejection process and the early evolution of planetary systems. The James Webb Space Telescope, launched in December 2021 and operational since mid-2022, is already contributing to rogue planet science. Webb's infrared capabilities allow it to study the atmospheres of young planetary mass objects in star-forming regions. Its spectroscopic instruments can detect the absorption and emission lines of molecules like water vapor, methane, ammonia, and carbon monoxide in these objects' atmospheres, revealing their temperatures, compositions, and weather patterns. In September 2023, Webb observed 6 candidate rogue planets in the NGC 1333 region of the Perseus molecular cloud, about 1,000 light-years from Earth. These objects, with masses between 5 and 10 times Jupiter's mass, appear to be forming in isolation rather than in circumstellar disks. Webb spectra will reveal whether their atmospheric compositions match predictions for isolated formation or whether they show signs of formation in disks followed by ejection. Ground-based telescopes are also advancing rogue planet science. The Vera C. Rubin Observatory in Chile, formerly known as the Large Synoptic Survey Telescope, began operations in 2025. Its legacy survey of space and time, LSSD, will photograph the entire visible southern sky every few nights for 10 years, creating a vast database of astronomical observations. While not specifically designed for rogue planet detection, LSSD data will enable searches for nearby cold rogues through their proper motion, their apparent motion across the sky relative to background stars. The extremely large telescope, ELT, currently under construction in Chile's Atacama Desert, will have a primary mirror 39 meters in diameter, the largest optical telescope ever built. When it begins operations in the late 2020s, ELT will be capable of directly imaging exoplanets orbiting nearby stars and potentially very nearby rogue planets if they are warm enough to emit detectable infrared radiation. Its adaptive optic systems will correct for atmospheric blurring with unprecedented precision, producing images sharper than Hubble's from the ground. The Square Kilometer Array, SKA, mentioned earlier, will revolutionize radio astronomy when its first phase becomes operational in the late 2020s. If rogue planets emit detectable radio waves through auroral processes or other mechanisms, SKA will be sensitive enough to detect them from distances of dozens of light years. This would open an entirely new window for studying rogues, complementing optical and infrared observations. Interstellar missions, though still in the concept stage, could one day visit a nearby rogue planet. The Breakthrough Starshot Initiative, announced in 2016, aims to develop light sail propulsion that could accelerate small spacecraft to 20% the speed of light, enabling journeys to nearby star systems within human lifetimes. If a rogue planet were discovered within a few light years of Earth, certainly possible given the predicted population density, a similar mission could reach it within decades, sending back close-up images and data. Such a mission would face unique challenges. Unlike planets orbiting stars, which should be observed from a distance to determine their positions and predict their future locations, a rogue planet's trajectory would need to be measured very precisely over several years to calculate an intercept trajectory. The spacecraft would also receive no solar power in the vicinity of the rogue, requiring nuclear or other independent power sources. The scientific return from such a mission would be extraordinary. Direct measurements of a rogue planet's mass, composition, magnetic field, and surface conditions would answer fundamental questions about these objects. If the rogue had a subsurface ocean, instruments could potentially detect it through measurements of the ice shell's thickness, electromagnetic sounding, or detection of water vapor plumes if any cracks penetrated the surface. Closer to home, advances in theoretical modeling continue to refine our understanding of rogue planets. Modern simulations of planetary system formation, run on supercomputers at institutions worldwide, include thousands of planetesimals and track their interactions over millions of simulated years. These simulations reveal the chaotic nature of early planetary systems and quantify the efficiency of planet ejection under different conditions. One surprising result from these simulations is that planetary systems with specific architectures, such as multiple giant planets in compact orbits, are particularly prone to ejection events. Systems like TRAPPIST-1, with 7 Earth-sized planets orbiting very close to a small star, appear dynamically stable now, but might have lost additional planets during their formation. Statistical analysis of known exoplanetary systems could reveal signatures of missing planets ejected in the past. Another area of active research involves the long-term evolution of rogue planets. As these objects age and cool, their internal structures change. Gas giants contract slowly over billions of years as they radiate away their formation heat. Rocky planets might develop thick crust layers as their mantles cool and solidify. Understanding these evolutionary processes helps astronomers predict the current state of rogues ejected at different times in the galaxy's history. Astrobiology, the study of life in the universe, increasingly considers rogue planets as potential habitats. Research into extremophiles, organisms that thrive in Earth's most hostile environments, informs predictions about what kinds of life might exist in rogue planet oceans. Hydrothermal vent ecosystems, Antarctic subglacial lakes, and deep subsurface environments all provide analogs for conditions on rogue planets. Laboratory experiments simulating rogue planet conditions test the limits of life. Researchers grow microorganisms in darkness at low temperatures with limited nutrients, studying how they adapt and what biosignatures they produce. These experiments guide the search for life by identifying chemical or physical markers that might indicate biological activity in rogue planet oceans. Ratios of isotopes, specific organic molecules, or unusual distributions of elements. As technology advances and our observational capabilities expand, the dream of directly imaging an Earth-like rogue planet, perhaps even detecting signs of life in its subsurface ocean, moves from science fiction toward possibility. It may take decades or centuries, but each discovery brings us closer to answering profound questions. How common are these wandering worlds? Do they harbor life? What secrets do they carry from their birth systems? What stories could they tell of their journeys through the galaxy? Rest now in the knowledge that humanity's exploration of the cosmos continues, that each generation builds on the discoveries of the last, that the mysteries surrounding rogue planets are slowly yielding to patient observation and careful thought. The future will bring answers we can only imagine today, revelations about the universe's hidden populations, confirmation or refutation of our theories, and undoubtedly, surprises we haven't anticipated. As our journey through the realm of rogue planets draws to a close, we return to the larger perspective, the place these wandering worlds hold in the cosmic story. They remind us that the universe is far more complex and dynamic than our everyday experience suggests, that between the visible stars lies a hidden population perhaps outnumbering those stars, and that the processes shaping the cosmos operate on scales of space and time that challenge human comprehension. Rogue planets are not anomalies or curiosities. They are an integral part of how planetary systems form and evolve. Their existence reveals the chaotic nature of planet formation, the violence of gravitational interactions, and the ultimate expendability of individual worlds in the grand scheme of galactic evolution. Yet each rogue carries with it a unique history, the chemical signature of its birth cloud, the scars of gravitational encounters, perhaps even the memory of life if it once orbited in a star's habitable zone before ejection. Consider the timeline. Our universe is approximately 13.8 billion years old, according to measurements of the cosmic microwave background by the European Space Agency's Planck satellite. The first stars formed within a few hundred million years of the Big Bang, creating the first heavy elements through nuclear fusion and scattering them into space when they exploded as supernovae. These elements, carbon, oxygen, nitrogen, iron, and many others, are essential for planet formation and life. The oldest known planets in our galaxy are nearly as old as the galaxy itself, around 12 billion years old. These ancient worlds formed when the universe was less than 2 billion years old, in an era when galaxies were colliding and merging frequently, when star formation rates were much higher than today, and when the chemistry of the cosmos was still evolving. Some of these ancient planets were surely ejected to become rogues, and they have now been wandering the galaxy for 12 billion years, 3 times longer than Earth has existed. Think of what such a planet has witnessed. It has traveled through the galaxy multiple times, circling the galactic center perhaps 50 times as it moves through the spiral arms. It has passed near supernovae, watched stars be born in molecular clouds, and drifted through regions of space where galaxy collisions created bursts of star formation. It carries within its structure and composition a record of the galaxy's chemical evolution, a time capsule from an era when the universe was young. The Milky Way itself is constantly changing. Our galaxy collides and merges with smaller galaxies regularly on cosmic timescales, the most recent major merger occurring several billion years ago. Currently, the Sagittarius dwarf elliptical galaxy is in the process of being consumed by the Milky Way, its stars and dark matter being stripped away and absorbed into our galaxy's halo. Rogue planets from Sagittarius are likely among the wanderers in our galaxy now, immigrants from another stellar system entirely. In approximately 4 billion years, the Milky Way will collide with the Andromeda Galaxy, our nearest large galactic neighbor. Computer simulations of this collision, which astronomers refer to as Milkomeda, predict that the two galaxies will pass through each other, their stars intermixing but rarely colliding due to the vast distances between them. However, gravitational interactions will fling countless stars out of both galaxies into intergalactic space, creating a halo of exiled stars around the merged galaxy. Rogue planets will share this fate. During the Milky Way-Andromeda collision, gravitational interactions will eject not only stars but also rogue planets, sending them into the void between galaxy clusters. These intergalactic rogues will wander the truly empty regions of space, where the nearest star might be millions or even billions of light years away, and the only light comes from distant galaxies scattered across the cosmic horizon. What would it be like to exist on such a world in intergalactic space? The sky would be utterly black except for faint smudges of light. Nearby galaxies too distant to resolve into individual stars. The Milky Way and Andromeda, now merged into a giant elliptical galaxy, would appear as a faint oval glow containing hundreds of billions of stars, but seen from such distance that they blend into a smooth luminescence. The silence and isolation would be absolute. The nearest physical object, perhaps light years away, the nearest star-hugging planet millions of light years distant. Yet even in intergalactic space, the rogue planet would continue its existence, its internal heat slowly dissipating over trillions of years, its geological processes winding down at imperceptible rates, its subsurface ocean, if it has one, gradually freezing from the bottom up as the core cools. Life, if it ever emerged in that ocean, might persist for billions of years, evolving in complete isolation, perhaps developing intelligence and technology, perhaps discovering the stars through their radio emissions or neutrinos, perhaps never knowing that other life exists in the universe because the distances are too vast to cross. This scenario, though speculative, illustrates the profound loneliness and resilience implied by the existence of rogue planets. They endure because endurance is built into the physics of planetary bodies, their mass, their composition, their internal heat budget. They continue because continuation requires only the absence of destruction, not the presence of purpose. They exist as silent witnesses to the universe's vast indifference, neither mourned nor celebrated, simply present, adrift in the darkness. But we, knowing of their existence, can celebrate them. We can recognize in rogue planets a metaphor for resilience, for the persistence of matter and energy following physical laws across spans of time and space that dwarf human history. We can find in their story a reminder of the universe's vastness and variety, of the countless phenomena occurring beyond our direct observation, of the richness hidden in what appears to be empty space. Rogue planets also challenge us to expand our conception of habitability and life. The traditional picture of the habitable zone, the region around a star where liquid water can exist on a planet's surface, may represent only a fraction of potentially habitable environments. If life can exist in subsurface oceans heated by internal planetary processes, then habitable worlds may be common throughout the galaxy, scattered through the darkness, each one a hidden oasis in the void. This possibility suggests that life might be far more common than we have assumed, but also far more isolated. Two biospheres existing in subsurface oceans on rogue planets light years apart would have no possibility of interaction, communication, or even awareness of each other's existence. Each would evolve independently, perhaps developing intelligence, perhaps not, but forever separated by distances that no organism could cross, no signal could bridge in less than years or decades. In contemplating rogue planets, we confront questions about meaning and significance in a vast universe. What does it mean for life to exist if it can never know about other life? What value do the world have if no one observes it? These are philosophical questions without definitive answers, but they invite reflection on our own existence and the cosmic context in which we find ourselves. We are privileged to live on a world that orbits a stable star, that receives abundant energy from that star, that has maintained conditions suitable for life for billions of years. We have developed technology to observe the universe, to detect planets we cannot see directly, to imagine what worlds we will never visit might be like. In this, we are the universe's way of knowing itself. Consciousness emerging from matter and contemplating its own origins and fate. Rogue planets, wandering in darkness, may never be observed or understood except by us and whatever other intelligences exist in the cosmos. Our curiosity about them, our efforts to detect and study them, our speculation about what they might harbor. These activities give rogue planets a significance they would not otherwise have. We are storytellers as much as scientists, weaving narratives that make sense of observations, creating meaning from data. As you drift into sleep, carried by these thoughts like a rogue planet carried by galactic currents, let yourself feel the connection to the cosmos. You are made of star stuff, as Carl Sagan famously said. Atoms forged in stellar cores and scattered into space by supernovae, eventually incorporated into a rocky planet orbiting a yellow dwarf star, organized by biology into a conscious being capable of contemplating its own origins. The rogue planets, though isolated and dark, are your cousins in a sense, assemblages of the same fundamental particles, governed by the same physical laws, existing in the same universe. Their journey is not so different from yours, beginning in chaos, moving through time, experiencing changes, persisting despite challenges, and ultimately returning to the cosmic inventory of matter and energy. Rest in the knowledge that the universe is vast and strange and beautiful, full of wonders we have discovered and wonders still hidden, from the smallest quantum fluctuations to the largest galactic superclusters, from the briefest particle interactions to the longest stellar lifetimes. Rogue planets are one chapter in this grand story, the quiet wanderers drifting in darkness, carrying on their silent journeys, patient and enduring, witnesses to eternity, until the last stars fade and the universe grows cold and still, and all that was becomes all that will ever be, matter and energy transformed but never destroyed, continuing in forms we cannot yet imagine, into futures beyond prediction or comprehension. Sleep now, traveler, and dream of distant worlds.